All right, so let's look at, I'm probably, depending on time, I'll look at two problems. Maybe least mean square estimation and maybe the one of the homework problem. Can you hear me there?
Yes.
See you on each one. Can you hear me well?
Yes, yes.
Okay, very good. So let's look at this problem Ax equal to B. So it comes up, remember A is a matrix. So X is a vector and B is a vector. So X is of course the unknown and B is the data which is known. X is unknown. And A is a linear model. Remember, it being a matrix, it has got m rows and n columns. So A could be, A is a matrix, m rows, n columns. So there are three cases, m equal to n, m greater than n, m less than n. So remember, then there is unknown x equal to data. Of course, you know, if this is n, this is n by 1, and this is m by 1. So that's the size, right? So this case, you look at here, if, or let's say, if n is greater than m, n is the size of the unknown, n unknowns, m data points. So number of unknowns is equal to n. So if n is greater than m, we call this underdetermined. In other words, there are more unknowns, not enough data. And in this case, it is overdetermined. You have overdetermined. So this will be the case, pictorially it will look like this. Overdetermined. So look at it, this is a overdetermined because you measured lots of data, more data. And this underdetermined means it is like this. You have a lot of unknowns, but you are only able to measure few data points. And in this case, the number of unknowns and number of, you just measured enough data. That's m equal to n. So this is n by n. And then now comes the rank of the matrix A also into play. Anybody, what is rank? I'm going to denote it by rank, m. What is the rank of a matrix? Anyone?
The number of vectors in linearly independent vectors.
Yeah, in where? In A, right?
Yes.
So A has how many columns, how many rows? This case.
If m is greater than n, then the rank should be n.
How many rows and how many columns in a matrix? Look at this.
M rows and n columns.
Yeah, so obviously one number will be greater than the other, they are equal, or they are equal, right?
Yes, Professor.
Right. So whenever the number is, so what are you saying? In this case, look at this. So I'm going to write the columns as A1, A2, An, always n columns. Here A1, A2, etc. Except n is larger here. So this you can think of as vectors. So what would be here? Of course, the columns are A1 through AN also. So what will look at the way this? Let's take this case. There are n columns, but more rows. So what could be the rank of these columns in vectors? Anybody?
It's no greater than n, the number of columns.
Could it be less?
Yes, could be.
Right. So that this matrix may have n columns, but its rank could be less than n. So how about here? It has n columns. So what is the rank of A?
Less or equal to n.
So there are two cases we need to consider: rank equal to n, rank less than n. That is true in all these cases. And what is the rank of B? Anybody? B is a vector, obviously. What?
1.
Yeah, that's correct. It's a vector 1. So you see, look at this equation. I'm going to rewrite it in a different form in the next page. So I have A1, A2. These are vectors, AN. This is A, multiplied by x1, x2, etc., xn equal to B. So I can rewrite this as A1, x1 plus A2, x2, just by multiplying. Plus, this is another way to write this equation. What does this tell you about B? Anybody? What does this mean?
The vector B is in the column space of the
All right, so that is the first observation. If AX equal to B, then vector B so this is the same as saying, so if you have, so what will be the rank of these two? If B is in the column space of A, what will be, if I put B next to A, what will be the rank of this matrix? Anyone?
the rank of A.
All right, so we have this property. If that is true, then these two ranks will be equal. Okay, so that's the first thing. Some of you may not know this. So if you give this is only if this equation is true. If you are given an equation to solve it, if this equation is true, then obviously, as we can see from here, B is in the column space of A, or these two ranks are equal. But in general, let me ask you this. In general, if I give you a matrix A, and then I take a vector and put it next to it, does these ranks have to be equal or no? In general, I take a matrix, it has some rank, then I put a vector next to it and look at the rank of this matrix. Will they be always equal? Not this problem. I'm saying if I take a matrix, yes or no?
Yes.
No, not always.
Okay, so this doesn't have to be true always. So if this is not true, that means Ax is never not equal to B. That's what it means. So these equations, if this is true, then these equations are called consistent. So let me give you what is consistent equations. These equations are consistent. These equations are not consistent. So let me give you a geometric look at this equation: x1 plus x2 equal to 1. So that's this equation. So this is, let's look at 2 dimension. So x1 plus x2 is 1, and I will say x1 minus x2 is 0. That's the, so that will be this line. So these two, and then I say x1 plus 2x2 equal to 3. I give you 3 equations. So if I write it, I can write it like this. So x1, x2 here. So this is 1 minus 1. I'm reading from here. Then 1, 1. Then 1 and 2. And well, so let's see where is the third line. So when x1 is 0, when x1 is 0, x2 is 1.5. This is 1. This is 1. So 1.5 is here. And so remember, this point is 1, 1. So when x is 1, x2 is 1, x1 is 1, x2 is 1, this is 3. I'm sorry, when x2 is 1, this is 2, 3 minus 2 is 1. So when x2 is 1, x1 is 1. So this equation, another way is when x2 is 0, x1 is 1. So this is also, when x2 is 0, x1 is 3. When x2 is 0, x1 is 3. So where does this equate? When x2 is 0, hold on. When x2 is 0, x1 is 3. When x2 is 0, x1 is 3. So that will be somewhere here. And when x1 is 0, x2 is 3 by 2, which is 1.5. So this equation is 1.5 and 3 by 2. So that goes like this. So you see, these three equations are not consistent. I'm just giving you an example. So this should be 0.5, right? Because when x1 plus x2 is, when x2 is 0, x1 is 1, okay? So when x1 is 0, x2 is 1. So these two are 1. That's this equation, x1 plus x2 equal to 1. And this is x1 equal to x2. So that goes like this. Third equation is x1 plus x2 equal to 3. So put x2 equal to 0, x1 is 3, so I marked it somewhere here. Then put x2 equal to 0. Right, put x1 equal to 0, x2 is 1.5, so that's somewhere here. That doesn't go through. So these are not consistent equations. So you can see here if you call this to be A, this to be B, this equation cannot be true because they are not consistent. Let me give you an example of a consistent set of equations. So what I'm trying to say is, if you cannot just so let's see here again, I'll take the same equation, x1 minus x2 equal to 0 and x1 plus x2 equal to 1. So you have one equation, another one, 1. And let's say
Professor, by consistent equation, do you mean they have like a unique solution, all these equations?
So consistent equation is, so another way is to see, it will go through this, so or something like this. So what is this equation? x1 equal to 0.5, right? Or 2x1 plus 2x2 equal to okay, so x1 equal to 0.5. So these are consistent equations because I can write it again like this, right? So here you can see that whatever is rank of A is 2. In this case, you can check that rank of A is 2. But rank of A comma B is, you can check it out. Remember, it's a 3 by 2 matrix, so its maximum rank is 2, but you can see there are 2 linearly independent rows and columns, and this is 3. If you put A next to B, then this is you can check it out. Look at the eigenvalues or whatever. So these are not consistent equations, whereas here 1, 1 equal to x1 plus x2 equal to 1, x1 minus x2 is 0, x1 is 0.5. So this is so you bring this to, and if you check here, rank of A and rank of A comma B will be equal. So we have to deal with all these cases. What I'm trying to say is this will be the picture of a consistent set of equations. Everything goes through one point. If Ax equal to B, and this is the picture of a non-consistent set of equations. So there is no, so you have to, you are in 2 dimensions. So if you have a case like this, you can pictorially see, you can, so this will be the case. Here you have like this. Remember, if I give you an old equation, you can't see this, but what you can check is the rank of A and the rank of A comma B will be equal. This will be equal here. Whereas here rank of A is not going to be equal to rank of A comma B. What was the question? Do you understand now? Non-consistent equations. Here consist. So you can make measurements. Maybe because of the noise, etc. Everything is, the model is not being exactly validated. Remember. So in any case, we will like to get a. So of course, if you say X equal to B, if this is true, then this is, you are assuming that the equations are always consistent. But when you make the observations, it could be, maybe you are only like this, where here Ax equal to B. But here too many equations and only few unknowns. And the other extreme is like this. Let's say you are in a 3 dimension, right? X, Y, Z, and you only have 2 equations. So this is X plus Y plus Z equal to something. This is x minus y plus z equal to something. Only 2 equations, but you have 3 unknowns. So this will be like this. So you can clearly see here, with the 2 equations, you cannot solve for 3 unknowns. You cannot. So this is underdetermined system, underdetermined. Whatever, you try to make observations, but before you could make all the observations, whatever, things moved away or things changed, etc. Whereas here you have a lot more equations than you need. So the question is, can I use all these equations to solve this? Technically, you can say I only need n equations, but usually we may collect more data simply because the data may be poor, etc. And you may have, this case may become this case. This may be in truth there is a solution, all this should have gone through this, but because of the noise or something, this case will, this is in practice. So all this can happen. Ideally, everything should have gone through because there is a solution. But when you make the measure the data, things go bad. This is because this B is bad or it has error in it. So all these cases we want to address. So the key important thing to remember is adjust this with the picture. If the equations are consistent like this, then this condition is true. Remember, this is an algebraic condition, this is a geometric condition. You can look at the picture. If this is the case, if the rank, or if this is the case, then this is not going to be true. All right, so in all these cases, I am going to show So let's take consistent case, then I'll do the inconsistent also. So if Ax equal to B, then remember, if this is true, then of course I said rank of A is the same as rank of A comma B. Okay, this is another notation for rank. Then you can also write this as in this form, right? So if Ax equal, then you need so you can find, if they are consistent, you can find an equation of this form, I mean a vector of this form, call it y, and if you call this to be A tilde, then this is the same as saying that A tilde y must have a non-zero vector as the solution. So we need to find out that case. So let me first take the case where rank of A is n. So if Ax equal to B, remember A could be like this. So if this is M, this is N. This means A is, as you said, A has column rank. So Ax is B. I'm going to multiply by A transpose. So I'll multiply by A transpose. But A transpose A is, look at it, n by n, and the full rank. So I can multiply by the inverse of that from here. So I'm going to do A transpose A inverse the into this into here. So that's A transpose A x equal to A transpose A inverse A transpose B. But you can see this cancels with this, giving x is the solution is going to be this. So this is known as the least mean square solution. And I'll go over this one more time in a slightly different way. But you can see clearly this is not going to work if A is not a full rank. So let's take that important case. And we have a rank of A is some r less than n. So A is already, if as you know, if rank is less than n, then there is no unique solution, because if rank of A equal to R is less than M, then you can find a vector like this. All right, why is this true? So I'm going to look at I hope you remember what we did. You take any matrix, singular value decomposition. What we said last time was this. Now, if you are saying, why is this true? You have to go back to whenever we talked, last Saturday or Sunday, we did this, and this is going to be useful. So remember the properties. These are unitary matrices. In other words, U transpose is I. V transpose is I. U is U1, U2, etc. UM. These are vectors, orthogonal vectors. So UI transpose UJ is 0. Same thing for V. V is V transpose will be, these are column vectors. V transpose is row vectors. V1 star, V2 star, this way. Vn star. And Vi, Vj also 0. These columns are orthogonal. So you can see here, maybe I'll use a different. So look at this here. I'm going to squeeze in here. If I take one of these, remember this is beyond VR. This is VR star, VR plus 1, etc. Let me take one of the vectors from here, Vn star. So I'm going to do AVN. I'm not Vn, Vi. Vi is from here. I is greater than R. Okay, I'm going to take one of these indexes. Then you see A is this. So I'm going to multiply by Vi here. Vi here. Remember Vi, so I'm going to multiply Vi here. So look at here. This is V1 star. So this is going to be, look at what happens if I multiply this with this. This will be 0 everywhere except a 1 here. It will be all zeros because V1 star Vi, V2 star Vi, VR. And this 1 is beyond the VR. So then I multiply by this matrix, all this will be 0. And this is all full of zeros here. So I hope you can see that this whole thing is equal to 0. So what when we do a singular value decomposition, so that's the whole point. If the matrix is rank R, then there is always a vector Vi, which one of these vectors will make this matrix go to 0. AVI will be 0 for I greater than R. So if that is the case, remember, they are consistent. If Ax equal to B, then consistent means this is true. And also if rank A is less than, rank A equal to R is less than M, then we just found that there is a vector which will make this 0. So then you see, if X naught is a solution to this, then Ax naught plus Vi is also a solution because Ax naught plus AVI, but this is 0. So this is just B, Ax naught is B. So what are we trying to say? The solution to Ax naught equal to B is not unique. If rank of A is less than M, less than N. I hope you see my first point. The solution, if the rank is less than the number of columns, then there is no unique solution. So we are going to give you a unique, we can make the solution unique. So if you insist that I want a minimum norm solution, then we can make the solution to be unique. I hope you see that this is a solution. This solution is not unique. If rank is less than N. But I'm going to show that we can make it unique by so what is the problem? Let me define the problem. We have a consistent set of equations. that means rank A, or I'm going to call it row A, is the same as rank A comma B. So this is true, this is given to us. But we also know that rank A is R, which is less than, let's say A is M by N. Let's say M is greater than N. So you have more equations. So R is less than N. So we want to find a solution x naught such that ax naught equal to b and x naught has minimum norm or minimum energy. In other words, we want this quantity minimum. Remember, the solution is not unique here. Solution is not unique if the rank is less than R. So we are going to minimize. Any questions? Anybody?
Yes, Professor. So you said the solution is not unique. So is there a way to find out like how many solutions there will be?
Infinite number, right? Look at here. I'll tell you the reason. Look at our argument. We can take VI from any one of these, right? Spaces. Any one of these vectors, if you put it here, that will be 0, right? I went through this, right? So,
Yes, yes.
yeah,
Right.
so if you have here n minus r vectors, and you can create, in that space, you can create any linear combination. If you put it here, that's going to be 0, right? So that will be infinite number of vectors there. You see?
Yes.
All right, very good. So
Thank
the
you so much.
question is, what is it?
But there is also possibility that there is no solution at all, no?
No, there will be all, there will be, if the equation, that's what I'm going to show. So remember what I'm going to show. If the equations, if you have a consistent set of equations, okay? Let's make sure what you are right. If you are saying these equations don't match, that's a different, is that what you are saying, or they match? Hello, what are you saying? What
No, I
is the
was told
geometry?
when the rank is lower than n, there is either infinite mini solution or no solution at all, no? Like,
Why would the infinite solutions are there? Why would there be no solution? Remember, first of all, we are dealing with the case on the left side, okay? We are dealing with, let's read what is written here. We are going to solve this problem, ax equal to b. When you say equal to b means, what does it mean? We have a set of consistent equations. If this condition is true, right? So you can check, you can put a rank A and you take rank A comma B. If they are equal, then the equations are consistent. I'm going to show that there is a unique solution. I mean, the solution is not unique, but we can, if you insist on, why are we going through all this? We went through this before, right? So ax not equal to b is the same as, if the rank is less than that, then there are a lot of infinite number of vectors solving this, so you add that to any x naught. So if x naught is a solution, x naught plus vi is also a solution. So there will be infinite solutions. The question is, how do you make it unique? So look at, I'm going to minimize this now. Excuse me. So I'm going to minimize this, and remember A is U lambda B star, so I'm going to substitute for A. This is where the singular value decomposition helps. Remember, norm A, I hope you know this, and the norm of A squared means A transpose. So if you multiply by a unitary matrix on this side, so norm of A minus B squared is A minus B multiplied by its transpose, A transpose minus B transpose. So if I multiply by U here on the left, so if I have UA minus B squared, I hope you, so that's going to be UA minus B so you can write this way, or you can write it the other. So it's going to be the trace of this. I'm sorry. So the trace of this. Trace is the same as trace of AB is the same as trace of BA. So you can also write this as A transpose B transpose multiplied by A minus B. So if you want, you can write this as the trace of this multiplied by U or UA B. So if I transpose this, you get, so a couple of ways you can do this. See, if you pull out U from here, you can write this as U goes outside. U transpose is identity. So you can write this as in this form. And I pull out U from here. So this becomes U star then the whole star here. Remember, there is a star here. All I did was this. I pulled out U outside. So U star is I. U star is I. So yeah. So I pulled out U outside. So this is UA. This is U star is I. So this is UA minus B. That is still the same. So I will write it here. Trace of U pulled outside, so A minus U star B. And here I'm going to pull out U outside, A minus U star B. Now there is a star. When I put this star here, this will flip. So this will become A minus U star B star. Then you have U star. Then you have U from here. So A minus U star B. But U star U is identity. So this becomes trace of A minus U star B multiplied by itself. Star here, A minus U star B. But that's the same as A minus U star B. So what is my whole point? My whole point is to show that if I pull this U outside, this will come and sit here as U star. I'm going to use it here. I hope you see this slight manipulation. So let's see here. I'm going to pull out this U. So this is the same as lambda V star X naught minus U star B. V star X naught is a vector. I'm going to call it Y. This is another vector. Let me call it C. So remember, Y is this form. Y1, Y2, etc., Yn, and C is C1, C2, etc., Cm. Because I hope you see what is going on here. U is M by M, this is M by N, this is N by N. So this will be M by M. This is m by 1, m by m. So the C will be also m by 1. So let me call this to V star. So Y is V star X naught. Remember, X naught is what we are interested in. And so I want to minimize this quantity, Ax naught minus B. So we brought it down to lambda Y minus C squared. Now lambda is a diagonal matrix. So I'm going to multiply by, so if you, what is lambda? Lambda is like this, lambda 1, lambda 2, up to lambda R. So if I multiply by lambda, look at here, you are only going to get, and if I call this to be C1, I hope you see the first equation is going to be lambda 1 Y1 minus C1. And that's a diagonal matrix. The next one is lambda 2 Y2 minus C2. So this matrix norm squared. And the lambda R YR minus CR. Then after that, this is all 0. So this is CR plus 1, etc. CR plus CN. So I'm going to write this. So I hope you see that this is lambda I YI CI squared, right? Absolute value squared of a diagonal matrix is square of the diagonal entries. I equal to 1 through R plus summation CK squared K equal to R plus 1 through M. So I hope, so just to quickly see it, what I wrote. So remember here, if you look at here, here you have freedom. And if you want to keep the, remember one requirement was we want to keep the norm to be minimum norm. And because the norm of X and norm of Y are the same. So you notice that only Y1 through YR we have, remember we want to minimize this quantity. So this quantity need to be minimized and the freedom is on YIs. This is where the freedom is. Lambda i's are given, CI's are given. And here there is no freedom. So of course you can make this quantity equal to 0. So you get YI equal to CI over lambda I equal to 1 through R. This is the only requirement we get, 1 through R. So this we are able to fix it here. So the question is, what about the rest? Now listen to my argument. So the argument is the norm of X naught is the same as norm of Y. Why is that? You can see because V is a unitary matrix. So the norm of this is this is the same as V X naught, because it's X naught star V star V X naught V star V is I. So these two are the same. So we want to minimize this quantity. These quantities you have no freedom. Here you have complete freedom. So set it equal to 0 so that the norm of Y will be minimum. So that's what I'm going to do here. I'm going to set the rest of the Y's to be 0 for I greater than R. I don't think you will see this in this much detail anywhere, the solutions, norm of X. Remember, that was the whole point. We wanted to minimize the norm of X naught. X naught is the original solution. So for that, I'm going to force these quantities to be 0. You can choose these quantities anything you like. So you ask me how many solutions are there. You have complete freedom here. You put any value here, this Ax naught equal to B will be satisfied. Of all the solutions, we are going to pick up the one with the minimum norm. That means we are going to put this equal to 0. So this we are forcing it to be 0. You can put them to be 1, 1, 1, 1. It doesn't matter. You will get the. So let me go with what you have. So you have Y, which is Y1, Y2, etc. YR plus 1, etc. Y n is going to be y1, of course, look at here. Y1 is Ci over C1 over lambda 1, etc. C2 over lambda 2, Cr over lambda r. The rest I am going to put the zeros. Now look at the manipulations I am going to do. So this I can write as 1 over lambda 1, 1 over lambda 2, up to 1 over lambda r. Then C1, where is C? A couple of pages back. C is from here. C is U star B, and U star means U1 star, U2 star, etc. UM star B. So C1 is U1 star B, etc. So this is C1 is U1 star B over lambda. Lambda 1 I took care of it. So this is U2 star B and etc. Yeah, here. So if you want, you can write here it as U1 star B over lambda 1, U2 star B over lambda 2, etc. UR star over B over lambda R. Then the rest is all zeros here. So I'm going to rewrite this in this fashion. U2, so UR star B, then the rest is all zeros. But I can do a trick here, watch now. So this is, the dimensions don't match because this is Y is N by, this is only R. So I'm going to extend this by adding zeros because this should be N by N, right? And this is, look at here, N by 1. So I'm going to, let me add zeros here. Otherwise, I have to stop here, right? So I'm going to make this is the same as 1 over lambda 1, 1 over lambda 2, 1 over lambda r. Then I'm going to add zeros so that to make it n by n. Then, see, it doesn't matter what I do. So I'm going to put it here, U1 star B, U2 star B, etc. And I'll UR star B. And up to UM star B, because because of this zero multiplied by, so this is because of these zeros to effectively come, I extended it by 0, then I can rewrite it in this manner. This is Y now. But if you recall, going back, Y is V star X naught. So this is V star X naught. So remember, we made it unique by forcing these zeros. These zeros are here. They have been forced here. And this, of course, this I can write it as now U star B, because U1 star B, U2 star is this matrix multiplied by B. Then you see I multiplied by V here. So this gives X naught. What we are looking for is V, this matrix inverse. I'm going to call it lambda inverse for now, U star B. But this is not regular lambda inverse because there are a lot of zeros. So this is called the pseudo inverse. So let me give you the nutshell solution. So you have A equal to U A equal to this. I'm going to call A inverse. I won't put inverse completely. I'm going to call it B Then I'm going to do 1 over lambda. I'm not going to invert all the diagonal entries because beyond some of them are 0. So I'm only going to do up to here. Then so I'll construct this matrix. This is known as the pseudo inverse of U star. Notice I flip the matrices. B comes here, U comes here. This is the Moore-Penrose inverse or etc. etc. Then what you have here is just that matrix. So you might have heard this solution and you might have used it also so many times. Or if you don't, if the equations are not consistent, just to do singular value decomposition and use the pseudo inverse. And here is the complete proof. So go back and read what I wrote, I think. So what we have is, if, let me summarize it. If AX equal to B, these are consistent. But rank of A is less than equal to R is less than the size, then no unique solution. No unique solution to AX equal to B. There are infinite solutions. We can make it unique by requiring by making X naught to be minimum norm. And it's given by that minimum norm solution. Remember, the minimum norm is forced here. This is where we are forcing the minimum norm. You have only, you can choose, you have no choice here, but here you can choose whatever you want. But we'll choose 0 to make this norm of Y minimum. Norm of Y and norm of X are equal. So that minimum norm solution is given by A pseudo inverse B. Any questions?
Professor, my question was like about this point, last point that you indicated, like A cannot be singular any minute, no way that the A can be singular matrix.
Of course, A can be singular. What do you mean? That was the whole point.
I mean, if rank R is less than N and A is non-singular, there is infinite many solution. But when A is singular,
hold on. I think you're mixing up. A is called a singular if the rank is less than its size.
but what if it cannot be inverted, like determinant of A is 0? Is it possible?
First of all, you are confusing. We are even doing more general case. You are consulting A is N by N, right? See, if the determinant of A is not 0, then A can be inverted, right? A inverse exists, right?
Yeah.
If the rank of A is less than N, then the determinant of A is 0. This is A is singular. This is called singular.
Mm-hmm.
In that case, if you do UDV, it will look like this. This is what A, right?
Okay.
In this case, hold on. In this case, if you UDV, A will look like this. It will have all the eigenvalues non-zero. In this case, there is no inverse, doesn't exist, but you have a pseudo inverse. Pseudo inverse is going to be, I gave it to you. You understand?
Mm-hmm. Okay.
There is no inverse here because if A is like, you cannot invert it, but you have a pseudo inverse. This pseudo inverse comes up in the least mean square solution. But we did actually even more general. We took a case, rectangular case. What if A is like this? What is the determinant? I mean, what is the determinant here? You have a set of equations. This is what we solved for you. if you remember. So here the solution is not unique. That was the whole point of going through all this. Did you understand anything?
Yeah. I got that.
And where is the confusion? Your question doesn't make me happy. So ask me.
I just no, I just got it. Like I was concentrating only on n by m metrics, like rather than more broad sense, like n different than m.
Yeah, mostly it is like this. You collect a lot of data, you come home, and you see that the data may not be, this may not be even true. This may be, this is what I'm going to do next. This may be only approximately true. But if you're lucky, these two will match. That means B and A have the same, A comma B have the same column rank. See, whatever it is, the model may be bad in the sense that A itself may not be full rank. You see that? That's what the solution we went through. See, just because you have a model, that may not be a good model. So if this is m by n, its rank, as you said, rank of A, if it is equal to n, you got lucky. What if the rank of A is less than n?
Okay.
Which case is true? I don't know. You both can happen, right? I gave you a set of equations, right? Look at this. Look at this A. I mean, here you don't have. Suppose I give you this A. What is the rank? Anybody?
The rank is 1.
Yeah, rank is 1. So you already have a problem with model. So I made 3 observations. Let's say I have, so these are the observations. All right, so you can see this is, everything is bad here because this is rank 1. And if you so rank of A is 1. If you look at the rank of A comma B, that is 2. Sometimes if you, or you may have another case where this is, so this is another case. Let me call this B1, this is B2. So if the data is like this is a consistent case because this and this have the same rank. If the data is like this, then you have an inconsistent case. And we haven't addressed this. We have only addressed this case. You understand? I'm only addressing this case so far. I'll come to this later. So I'm considering very general equations. Of course, if you have square, here you only have 2 cases. That means you have enough equations and enough unknowns, but the number of equations may be lower rank. That means they're all not that many. That means the model is no good. So the observations are not going to give you the unknowns uniquely. And you can make it unique by requiring it to be lowest norm. Anybody has any questions or any confusions? Or you have to go home and look at this or go through my lecture again. So I've done all this case. I'll summarize again. You have a case, nice case, this one. So this is n by n. So here rank of A is n. Then the solution is easy, unique solution, A inverse B, B1. Here the rank of A is less than n. Then what do you do? Anybody? We just went through it. Then the solution is not unique. This is not what we went through. But we can make it unique by requiring it to be minimum norm. In both the cases, of course, since it is square, this will always be in the column space. That solution is A pseudo inverse B. A pseudo inverse means a B star, I'm sorry, B, then here lambda pseudo inverse U star B. So this is, I think this is known as Moore, there are several names for this, Moore-Penrose inverse. Remember, we go through, this means you go through this 1 over lambda 1, etc., 1 over lambda r, then zeros. B used to. Any questions? So did you, I hope you understood what is going on, right? Yes, no? So this is a special case, square matrix. When it is it is square and lower rank, how do you solve it? That's what we just went through. So you can, then you don't have to worry about consistency, because I mean, when it is full rank, you don't have to worry about consistency. Otherwise, you have to again worry about consistency also. But if it is consistent, then the low rank solution is given by this. Any questions?
If A is a full rank and you try to compute the Moore-Penrose inverse, I guess would V and U transpose be scalar?
Look at here. No. A is U lambda V star. Lambda is lambda 1, lambda 2, etc., lambda n. Remember, A is full rank, so all the eigenvalues are non-zero, right? Yes?
Yes.
Then Moore-Penrose is the same as the regular inverse, because that's simply going to be V. You have the Moore-Penrose is 1 over lambda 1, etc., 1 over lambda n U star. So that's the same as A inverse. You don't have to worry about this. If A is full rank, you just invert it. What is the problem? The problem, the thing get messy only if A is lower rank in a rectangular matrix. Okay?
Okay, thanks.
Yeah. And so another way you can say is that yeah, any questions? You want me to go with this to the next case, or shall I go over to the homework problem, what we were discussing in the last lecture? There is one more thing here, but it gets complicated. I don't know how much you got this even. So the next one I was going to do is when the equations are not consistent. Hello? Give me some feedback. Did you understand what we went through? So other way, what we have went through is if we are given ax equal to b, I try to find a solution ax naught minus b, minimize this over x naught. So we are minimizing this error. And so the minimum error turned out to be if you that ck squared k is equal to r plus 1 through n. So if it is full rank, there is no error. This is the beyond the rank. Remember, somewhere we go back to our thing. And also we pick a solution so that x naught has norm is minimum. So not only we minimized this quantity, and we minimized with a vector which has got the minimum norm. So this we have accomplished. If ax equal to b, remember if ax equal to b means it's understood that b is in the columns rank of in the column space of A. So all this case we are dealing with equations of this form, consistent equation. They all pass through one point. That's the case we have been dealing with. This is overdetermined, this is underdetermined. In a three-dimensional space, it's underdetermined. Still, this will be the minimum norm solution. Now, what I want to do next is this case. You're given a bunch of equations, they are only approximately true. I'm going to write it like this. Most of the data, anybody makes any, you have a model, then you make the measurements. Most of the data is always going to be like this. The model is not going to, so set of equations that are approximately true. You want me to proceed or you want me to stop it? Somebody give me
Procedure,
a feedback.
please.
What?
Procedure, please.
Okay. So again, I want you to understand, if somebody writes like this, it means equations are, you should immediately keep in mind that this is true. If somebody gives you equations like this, you must be serious about this equality. If this equality is true, then B is in the column space of A. But what is interesting is still the rank can be the rank R can be less than M, the size of this. That's the case we covered this. So in all these cases, when R is less than M, then the solution is the best we can do is this solution, the pseudo inverse solution. So I'm just summarizing it. X naught equal to A pseudo inverse B is the minimum norm solution. So AX naught is another way to think of this is this is minimized. This is not going to be 0. This is simply sigma ck squared k equal to r plus 1 through n. And you know what these values are, m, I guess. These are we defined. You can go back and see. So the minimum the minimum norm solution, two minimums are going on. The solution, the norm of this is minimum, and we are minimizing this error. So if you call that final ax naught to be b hat, then what we are doing is we are finding a, another way to say is that we are finding a b hat such that b minus b hat is minimized. Do you see what I'm trying to say? If you want another interpretation. So listen to me, the problem again. This is the data. We measure the data. Data is consistent. Look at this. Data is consistent with the model. This is the model. So the data and model are consistent. That means this and this are equal. But still the model is low rank. That means the complexity of the model is not as big as you expected. You were thinking the complexity is m. No, I'm sorry. You were thinking the complexity is n, but this is less than minimum of m comma n. Maybe that's the best way to write it. So then we use. So the question is, you have solution. If you want a solution which minimizes this error, so if I call ax naught to be b hat, we are finding a solution with the minimum norm, which will minimize this. Other way to say it is that, remember, b is the data. We are making slight, this is the adjusted data, slight adjustments to the data. This is the original data. So we are making slight, because there may be slight error here in the B. So another way to look at this is you are making slight adjustments to the data so that you get a solution with the minimum norm. So that's the final interpretation I have. So x naught is A inverse B. We can think of this as B hat. Is modified measurements, modified data. This is the original data. So what have we done? We wanted to minimize ax naught minus b. This was minimized. So we did that. Minimization was on x naught. That is the same as we came up with this b hat, because a hat b ax naught. B hat is a x naught, right? And x naught is this. So remember, x naught is, what was it? V lambda inverse u star b. So this is what we called a hat. So if I multiply it by a, I'm going to multiply by a here. Here you have b. So this is your, this whole thing multiplied by a here. This whole thing must be b hat. So that's the b hat here, ax naught, which is the same as a pseudo inverse b. So this is the modified data. So what is my point? My point is you're finding a solution such that the original data is slightly modified so that this solution has minimum norm. And that solution is given by A pseudo inverse B. So one way to look at this is that you have modified the data. Remember, the data was what it was. But it was good data, except that you cannot invert the matrix because it is lower rank. So there are many solutions. So we picked up the one with the lowest solution. That's in effect, you're also changing the data slightly to fit that solution. Okay, so that's good. Now the big deal is this one. What if your data is like this? your measurements are all over. So this is not true anymore. I'm going to write it like this because this is the equation a11 x1 a12 x2 plus etc. a1n xn equal to b1. So you have the, but when you draw geometrically, it's like they are not meeting anyway. This is consistent. Everything is going through one point. So looking at this picture, you may say, oh, this looks like a solution, or this may be a solution. So this is, so we want to find out a solution. The question is, can you, so where is the error here? So you can say, see, previously, if you look at here, we are adjusting B to B hat. Original data is modified. That means the assumption here is data may have error. That's why we adjusted the data. See, the data got adjusted. So that the solution turns out to be unique. Here I'm going to say that I don't know, maybe I'm going to assume there is error both the places. So this is the, this gives you maybe most of you have not heard about this. So this is the, and once you understand the singular value decomposition, you will understand this one. Anybody have heard about TLS? Anyone? Total least square? Yes? No?
Professor, could you show an example of how to get the pseudo inverse of A?
All right. So you have to do, you can do in MATLAB. So A is a matrix, some m by n, right? I'm not going to do it by hand, but you do SVD of A in MATLAB. It's going to give you three matrices, U, lambda, V. So you have to see how they write it. I think MATLAB may be writing it as U lambda V. I wrote it as V star. So that means my V is their V star. So it will give you these three matrices. And I think even in, I don't remember, but in the MATLAB, you have already the pseudo inverse command. So if you put inverse for a regular matrix, I don't remember the command for it. So the pseudo inverse is, remember, A is UDV. So A inverse is, so I write it as V star. I don't remember what they put it, either V or V star, you have to check. But its inverse is going to be, I just went through this, it's going to be there is a command for this. So this is the pseudo inverse. So you physically have these matrices here. V is sitting here, U is here, U is here. This matrix you have to physically invert the entries and put it back, whatever is this, according to the size. So remember, if this is m by n, then this will be, remember, this is m by m, this is m by n, this is n by, you can adjust the, this is n by n. So this will be n by n, this will be adjust the zeros and so on. So this is n by m, and this becomes m by m. So do you understand? This is the way you compute the pseudo inverse. You have to do it. There is a single command for this, so you don't have to go through all this. But in principle, this is what you would do. But you physically have to do this. If you're asking me how to find, I went through all this, right? UIs satisfy these equations, right? You take the A is given, so you take the matrix A star. From that, you can construct all the U1 through UR. Then you fill up all the way through UM because A is m by m, right? A star is m by m.
Oh, okay.
And these eigenvalues are lambda 1 squared, lambda r squared. These eigenvalues are 0, but you can fill up And then I told you, I showed you how to find the vectors v1 through vr and beyond.
Yes.
And but you don't have to do any of this. You can use MATLAB routines.
Okay, thank you.
Yeah. So let me come to this total least squares. So you can see AX being approximately true. So let's say A is a full rank. A is like this. Nothing is, don't think of a square. Think of always more, you collected more data. That's why it is inconsistent. This is long. That's the data. There is a lot of data. And these equations, because of the measurements everywhere, these are only approximately true. But let's say the rank is n and it is inconsistent. I don't know whether the problem is with the model or with the data or both. So this is not exact. This is not true. So if I to find that, so what I want is I want to find out. I'm going to make small adjustments to A. So I want to convert how to do this. That's the problem. So A hat is A plus delta A, and B hat is B plus delta B. So unlike here previously, because it is consistent data, we only made adjustments to the data, smaller. Whereas here everything is bad, maybe. So we are going to make adjustments to A hat and B hat. Then if you do that, we can write it like this, right? This equation is the same as this, right? So I'm going to show you how to find an x hat and -1 so that this is true. If we can find this, then we have solved. This is what we want to do. Look, this is not equality here. So I want to find an x hat so that this is true, but I'm willing to make adjustments here and there because why this is not true, maybe this is bad, this is bad. You have to decide. If you say there is nothing wrong with the A, then just do this. So how do you do this? So I'm going to make it quick for you. See, previously we did singular value decomposition of A. A is U lambda B star. Now this is the total least square. I'm going to take this matrix and I'm going to do it's a singular value decomposition of B star. So this lambda star will look like this. No, let me maybe. So A is U B star. So lambda 1, lambda 2. I'm going to remember we already assumed A is rank n. So A is like this. But when we put B, remember they are not consistent. That means rank of A comma B is n plus 1 because these equations are not equal. So whatever is the rank, when you put one more, the rank of A is n, rank of A comma B is n plus 1. So I'm going to use that matrix, A comma B. Remember, it will have n plus 1 eigenvalues. So that is going to be like this. Lambda 1 tilde. It's a different matrix, so it's not going to be the same values. So let me write mu 1, mu 2, etc. Mu n plus 1. And here you have v1 star, v2 star, etc. vn star, vn plus 1 star. This is what we call v tilde star. So remember, we are doing SVD on A comma B, not A anymore. This was the SVD on A. So that's the new idea. My idea is to show that I'm going to create a vector X so that this is equality here. Here there is no equality, so I'm going to find a vector X. So remember, the rest is all 0 here. I hope it is clear. So the interesting idea is we brought this, we are ready to massage both A and B. And the idea is here, once again, look at here. I want to, so this equation is the same as this. So I'm going to find an x tilde and minus 1 such that this is 0 by making adjust. So look at what I'm going to do. From here, I'm going to create, you have to pay attention to what I am doing. I am going to make mu1, etc. I'm going to keep up to n the same. These, I put different values because these are not the same eigenvalues. It's not like all the eigenvalues are going to remain the same or singular values. They are completely different because this is a different matrix, A tilde. So look at what I have done. I'm only going to make a change here. The last eigenvalue I'm going to put to 0. And then I'm going to keep this, there is no change. There is no change here. So this is, so from MATLAB you have to find out these three matrices and force this to be 0. And then recompute these three values. And I'm going to call this to be so this will be the same size as this. So this will be some A hat, B hat. You'll get something, some matrix. The last column I'm going to write it like this. Because of this 0, previously when you remultiply, you are going to get some other numbers. You're not going to get the same numbers. Okay, now what? Now watch what I'm trying to do. So remember, the only difference between this line and this line is, and you will see why I did this. So let's pay attention to this vector. So that's Vn star, that's a row vector. These are row vectors. Right? Remember, these vectors are known because you know this, so you know this, you know this, you know this. All I'm going to do is I've just made this 0 and kept everything. I didn't reduce the size or anything, so that I'll get exactly the something else here. I'm going to call it A hat and B hat. Now let's just take this vector and multiply on this side and see what happens. So I'm going to so here I'm going to multiply by V n plus 1 here. Okay, so I'm going to do it here, V n plus 1. So I should multiply by Vn plus 1. So this is V1 star, V2 star, etc. Vn plus 1 star. I'm just copying. You have it there. I don't have space here. So I'm going to multiply by Vn plus 1 here, which I'm just writing in here. So notice that this multiplied by this is 0. This multiplied by this is 0 because these vectors are orthogonal except the last one. So when you multiply these two, you are going to get 0, 0, 0, 0, then 1. And then you have this matrix, which is mu1, mu2, etc., mun, then 0, 0, 0. And here you have u. See, now we multiply this. Notice that first row into first column, second row into first, etc. Then when you come here, there is a 1 here. All the columns, the last entry is 0. When you, this one, the last entire row is 0. So that multiplied by 0. So you can see if you multiply these two, you will get just all zeros. U multiplied by 0 is 0. So if I rewrite that equation, let's say this Vn tilde, this one from here, they all should have been tilde, but so let me go here. Remember, these V's are not the same, so I'm going to call something else here, a tilde here, because these V's are not the same. These should have, yeah, these V's are not the same. These V's are, of course, the same. This is A. This has got V1, V2, etc. This is V tilde. So I'm going to call it tilde with this. So this is also tilde here. So this is the tilde from this bigger matrix. So all these are tildes. And this is true. So we have A tilde. And let me write this Vn tilde here as V1, V2, etc. Vn plus 1. Remember, that's a matrix because of the original size. Look at the size of this. This is m by n plus 1. So this will be, this is of size n by n. This will be a size n plus 1 by n plus 1. I take the last column of that which is what I did here. I multiply. This is the last column. So I have this equal to V1, V2, Vn. I'm just multiplying by this because this multiplied by Vn tilde, I'm just writing it down, Vn plus 1 is 0. So I suppose I divide this throughout this scalar by minus Vn plus 1. So in other words, take this x0 vector to be Vn divided by minus Vn plus V1. This is V1, right? V1 divided by Vn plus 1 minus V2 divided by Vn plus 1 minus Vn divided by Vn plus 1. So this will be minus 1. So now if then I have this A tilde, B tilde multiplied by x0 is 0, where x0 is this. So what is the story? Look what I have done. We wanted to find a x0 such that this is true. Ax0 equal to b, we want to find out. So I have this one, Ax0, this is now x0 and minus 1. So if I call this to be, this is x, this to be x0, I can rewrite this as A tilde x0 equal to p tilde. So I found a solution. This is where we started with. Look at where we started with. Equations are not equal. I wanted to find a solution, and in this case, because A is rank n, we have a singular, a unique vector which will make this adjustment. So it made slight adjustments to both A and B such that you get this solution. This is your TLS solution. So if you do this, if you go home and do an example, where is my picture? You will get somewhere here. You'll get the TLS solution somewhere here. But you can eyeball it also. I can say, you can say, okay, because all the equations, if three equations are going like this, you will say your solution is somewhere here, right? If this is your coordinate system. If three, so TLS will turn out to be something like this. So what you are doing is you are making these equations make a slight adjustment. You're changing the equations so that they go through that model. So that's all I want to say about how much time we have. We have a little bit of time. Any questions before I move on? Hello. I also have, by the way, I have videos on YouTube on this topic. You can check total least squares. There is an explanation, maybe not this detail, but there is an explanation there. Anybody there? Any questions? No.
No.
Okay, what is the question? What is the question?
No question.
Is everything clear? So let's look at this problem. You have some homeworks going on, so I'll give you some quick. I think this is the last problem in. So I told you this yesterday. You collect sensors, you collect data. So you have some signal that you are interested in. By the time it comes to you, it appears as signal plus noise. So this you have some sensors. And you have no idea about this noise. So sometimes to estimate the noise, you put some sensors nearby and then estimate the noise. Remember, the noise is not exactly the same. So you may have a situation like this, signal plus noise, then when you try to measure the noise, that noise itself is contaminated. Or you may have a situation where you have the other signal is like this. You have one noise, a different noise. Or you may have copies of this. So I give you a couple of, all these problems are again discussed in YouTube. I think the solutions are there. So you just have to watch them. Try under least mean square or something, right? So when I stack this up, you can see I can write in this form. So I'll do two cases. I mean, you can make three problems of this is problem number one. These two together are problem number two. And then you can take this in problem number three. So let me set up the general and so on. And I think you can expect in one of these mini tests, not the next one, but pretty soon I'll give you a problem like this once you understand some variation which you will have to do. So I'm going to do one problem. So remember, so you have to realize that everything is maybe column matrix or row matrix depending on what it is. So you can see if you stack x1 and x2, this is going to be s plus n, n plus w. So you can write this as, I'm going to come into this, etc. So this is the signal part, this is the noise part, right? So I'm going to do a estimation. That means I'm going to multiply I'm going to use a linear filter such that S minus S hat is minimized. Minimization is on H. So S is even this could be a vector. So we are going to minimize the trace of this. And if everything is stochastic, then we'll do an expected value here. So minimize expected value of S minus S hat square. So that's the same as S minus S hat multiplied by its transpose, S minus S hat transpose. Trace of that, as I said, trace is because this could be a matrix, we want a scalar quantity. So that is minimization of the trace of expected value of S minus S hat is HX multiplied by transpose, S transpose minus X transpose, H transpose. So if I expand quickly, expected value of S transpose minus expected value of H multiplied by expected value of, what is it? Expected value of S transpose, then S multiplied by expected value of S X star H star minus H XS X star so this is the complex conjugate of this. Then the last then is plus H expected value of XX star H star. So this is RXX. So I can write this as RSS minus RSX H star minus HRSS star minus or plus, I think we went through this XX H star. So now if I told you what the half was. So you do singular value decomposition, take the square roots of the eigenvalues. So you can see, if you want to understand all this, you need a little bit of matrix algebra. So let me expand this. This is like A. This is A transpose, right? So that is RSX minus RXX minus half minus H RXX plus half multiplied by its transpose. So this is multiplied. Transpose is RXX minus half RSX star minus RXX plus half H star. So let me expand. There will be four terms. RSX minus half, that's plus half, RXX inverse RSX star minus this multiplied by this. So RSX minus half plus half, so that's H star minus this multiplied by this. Plus minus goes away, so that's H RSS star. Then plus plus H RXX H star. Notice that these three terms are the same as these three terms. That's the whole point last time I was trying to say. So what is it? These three I can replace by this minus this. So I'm going to do it here. So sigma squared is minimization of expected value of S minus S hat star squared is, I'll show you in this. Let me write it down, then you can check it. All I did was these three terms is this minus this, and then I plugged it in here for these three terms. So RSS minus this plus this. RSS minus this plus this. So if you want to minimize this quantity, remember minimization is on H. You can make this whole quantity 0 by plugging in H. So H should be RSX. So we can write it here. This thing should be equal to 0. So RSX, RXX minus half minus H RXX half should be 0. Or this should be equal to this. I multiply by the half here. So I get H equal to RSX RXX inverse. So this is the solution. And if this is 0, the minimum sigma squared minimum is going to be RSS. Remember the trace of that. Minus RSX or XX inverse RSX. So your job is in the both the homework and exam, apply these two and find out. You need to do this. So you are not going to walk into an exam and do these problems. So please practice at home. Let me do a couple of problems. I'm going to do. So what's the difference between the two problems? In the left case, you have signal plus noise. In the other case, I have two sensors. One case I measure the signal plus noise, then I have some idea about this noise. So the hope is, can I cancel this noise using this one? So we'll see. This will be adaptive noise cancellation. So let's look. So first you need to compute RSX. S is so this is expected value of S multiplied by this is your X. X is RSX is this one. So this is going to be expected value of S plus N star. So that's expected value of S squared plus expected value of Sn. So I'm going to assume signal and noise are uncorrelated. So this is simply the signal power. That's this one. Now we need RXX. So RXX is expected value of S plus N multiplied by S plus N star. So that's expected value of S squared plus expected value of N squared plus 2 expected value of Sn star. Again, this is 0. So this is sigma squared plus sigma n squared. So I'm going to use this. Here everything is simple. So H is simply RSX XX inverse. It's a scalar here. So this is sigma x squared over sigma x squared plus sigma n squared. So I can write this as 1 over 1 plus 1 over SNR, right? SNR is sigma s squared over sigma n squared. So now if you want to compute sigma squared minimum, so I found the filter. This is the filter. And the sigma squared is, so all it does is, what does the filter do? It's just scaling, it's just a constant. So your best estimate is H multiplied by X, which is 1 over 1 plus 1 over SNR. That's a constant multiplied by X. X is here. And sigma squared minimum is, you just need to use this formula. RSS, what is it? RSS minus RSX H, right? H star, I guess. So this is trace of RSS. Look at it. This is H. So H RSX star. So we have all of the RSS is somewhere here. The signal power. This is signal power minus H is here. Sigma S squared over sigma S squared plus sigma N squared. And RSX is here. That is sigma S squared. So you cross multiply, you should be able to see that so I'm going to leave it to you. I mean, this is what you're supposed to do in the homework. Now I'm going to do this problem and compare these two. Any questions? Hello?
So professor, for the R double X, you eliminated the 2E S N just cause S and N has their correlation, isn't it?
Yeah, so I'm making some assumptions. Everything is zero mean and they are uncorrelated. Generally, you can assume signal and noise or signal and noise. Okay. So assumption is expected value of S is zero, expected value of N is zero, expected value of W is zero, here both the places, and expected value of signal and noise is correlation is zero, expected value of signal W is zero, and the noise are also uncorrelated. Everything is uncorrelated. Signal power is S squared, etc. Sigma M squared is the variance. Sigma W squared is that clear? Hello?
Yes, very clear. Yes, professor.
So that's let's do this problem. Then I'm going to go home. Right? I'm already home, but we'll stop this. So, in the second case, we collect the data. So I'm going to our X is S plus N, N plus W. So I'm going to write this as. So this is where you need to solve some problems. So this is your signal vector, this is your noise vector. So first we want to look at the solution. Where was it? This is your H. So we need to compute each of these quantities. So RSX, S is this S is 1, 0. This multiplied by X. Remember, RSX means what? Expected value of S X transpose. So that's going to be, these two are vectors. So you have to do this correctly. 1, 0, S, then X is going to be X1, X2, stop. So let me do this for you. X already we wrote it this way. So I'm going to take the transpose of this. So expected value of 1, 0, S, and the transpose of this is 1, 0 and multiplied by S plus like this, N and N plus W star. Let's assume everything is real. So look at here. When you take the expectation, this is, here you are going to see, I hope you see it. You make sure, how do I get this? Okay, so maybe I made a mistake. So let me, I also got confused. So we want H equal to R Sx or XX inverse. R Sx is of X transpose. S is what it is. S is the signal. This is all we want to estimate. This is the unknown. So S stays as it is. X transpose is here. X1 star, X2 star. So this is going to be expected value of S. So watch what I'm doing. I'm going to substitute for, this is a 2 by 1 vector, right? Transpose. This is, I'm sorry, 1 by 2. So this is S plus N star plus W star, right? X1, X2. This is X1, X2. X1 is S plus N, which I put it here. So this hits this hits this. So I hope you see that this is expected value of S squared plus expected value of Sn. This is 0, comma, expected value of Sn plus expected value of Sw. Both are 0. So this is going to be, and this I'm going to assume it to be sigma squared 0. So that's your RSX. And then we need RXX. So that's going to be expected value of XX transpose. Each of you should do this by yourself. You see, even I am getting confused. X is 2 by 2. So this is expected value of X1, X2 multiplied by X1 star, X2 star, because X is X1, X2. So this is 4 entries, right? Expected value of X1 squared, expected value of X1, X2 star, expected value of X2, X1 star, expected value of X2 squared. So that's going to be, so X1 squared, X1 is the expected value of S plus N squared. Here expected value of S plus N, N plus W. Here expected value of S plus N, N plus W. Expected value of N plus W squared. Now I'm going to just do it here. Anybody, what will be the expected value of this quantity? So when you expand this, there will be 3 terms. Expected value of S squared plus expected value of N squared plus 2 expected value of Sn. Anybody? What will be this value?
You got RSS plus RNN.
Sigma S squared plus sigma N squared, right? Not R, the variance, right? Yeah, R0 of S, but let's call it sigma S squared. Yes? How about here? Anybody? When you expand, there are 4 terms.
Sigma n square.
What?
Sigma n
Sigma
square.
n square.
Sigma n square.
Sigma N squared, correct. Because there will be only 1 term N squared, everything else. And how about here? Same thing.
Sigma,
Right?
sigma n square.
And here,
Sigma n square
when you
plus sigma
expand
w.
this,
Sigma
huh?
n square plus sigma n square plus sigma w square.
there will be 2 noises. When you expand here, you get N squared plus W squared plus expected value of 2 and W. This is 0. So sigma N squared plus sigma W squared. So now you see I need to invert this matrix. So let me write it in the next page. So RXX is sigma S squared plus sigma N squared, sigma N squared, sigma N squared, sigma N squared plus sigma W squared. So now you need to find the inverse. So you can do this by hand. It's a determinant. Determinant is this squared plus this squared minus this squared. So what do you get? Sigma S squared multiplied by this. Sigma S squared multiplied by sigma n squared, and then you have sigma n4, so plus sigma n squared. So you make sure this is correct. And then you have here, now if you say, I don't know how to do the determinant, you better go home and do the find out all this stuff. right? This entry is flip and this becomes minus. Why am I doing all this? Because now I need to find h. So h is going to be rsx, rxx inverse. rsx we already had here. So I'm going to do it here. Okay, this is fine. Then let me do rsx is what? Sigma squared 0. So you do it here. This row multiplied by this. So I'm going to write the expression. First of all, the constant is the same. So let me call this to be this whole thing to be C. Some constant C. So this is going to be C. Then this row into the first row into first column. First row into second column. So you're going to get so the first entry is going to be what? First row into first column. You're only picking up this sigma n squared plus sigma w squared. First row into second column minus 6. So you got h. So what is your estimate? Is going to be hx. So h is c multiplied by sigma n squared plus sigma w squared and minus sigma n squared. X is x1, x2. So that's going to be some constant multiplied by sigma n squared plus sigma w squared multiplied by x1 minus sigma n squared x2. So I'm going to pull out this constant outside. Sigma n squared plus sigma w squared multiplied by c. Then you have x1 minus sigma n squared over. So what are we doing? Look at the problem. Let's not lose track of it. You have signal plus, then you have some of noise. So the best filter seems to be you take the original data, which is this. Then from that, a portion of this noise is subtracted out. So this is what this is adaptive. So you are cancelling out the noise. You are not cancelling the whole thing because you don't know how much noise is there. What is the contamination? And this is only a scaling, right? So let me see. So we pulled out sigma n squared plus sigma w squared outside. All right, so you can simplify this constant. So in any case, the best estimator is some constant. What you do is x1 minus some x2. This is going to be sigma n squared by sigma n squared plus. Interestingly, notice that this is a fraction, eta. This fraction is less than 1. It makes sense. So this was of the form s plus n. This is of the form n plus w. Because everything is stochastic, you can't just subtract it out. So the scaling factor is going to depend on the variances of that. So this is the best you can do adaptively.
Professor? I have questions previous pages. You in the first case. What is sigma one? Yeah, in the first case you say what is sigma one scale? I didn't catch it. Sigma one scale.
There is no 1 squared, sigma s squared. What do you mean?
There is the sigma.
This is the first case.
The first case, but you said the sigma one scale minus like sigma s.
Oh, yeah, here, no. This is not sigma 1. This is sigma s squared.
Oh, okay. Thank you.
Look at here, RSS, right? I just wrote it as.
Oh, thank you.
So if if you multiply, you can see this term cancels, sigma 4 cancels here, and you get this term.
Okay.
Okay, now I am going to compute the error, then we can go home. Then we will compare with Then remember this is case 1, so I'm going to call it sigma 1 squared here. That's this error. Let's see what is the error here. Remember here there was nothing to cancel. There is no dot. You only have here you have more data. So which error do you expect to be? You have sigma 2 squared. We'll compute this. Here you have sigma 1 squared. Which error you expect to be smaller between these two? Hello? Look at these two problems. Which error will be smaller?
Sigma 2 square.
Maybe, yeah, we expect this to be smaller because more data, you are doing more stuff here. So let's see. So we found the filter here. Now I have to find the error. What was the error formula? What was it? So sigma 2 squared minimum is, where is the error formula? Or so I'm going to use this formula, RSS minus H or SX transpose. RSS is sigma S squared, so that's easy. H is, where is H? We have H here somewhere. So you also have H. H is sigma S squared 0. And RSX transpose is, I'm sorry, yeah, H is, where is H? Yeah, H is here. So let me write it down. Sigma S squared minus H. H is here, right? So I'm going to, we know what is C. I'll come back to that. So H is C, sigma N squared plus W squared minus sigma W squared. Then RSX star. RSX is here, so that's simply sigma N squared, sigma S squared 0. So please check me. So this is sigma S squared minus this multiplied by this. So the numerator is sigma S squared multiplied by sigma N squared plus sigma W squared. And this, let me substitute for C somewhere here. So this was our C. I'm going to write it as sigma S squared multiplied by sigma N squared plus sigma W squared plus sigma N squared sigma W squared. So if I divide by this quantity, or let me cross multiply this. So take this, my God, and then so the numerator becomes sigma S squared. Then you have sigma N squared plus sigma W. I'm multiplying this with this. W squared plus sigma N squared, sigma W squared minus so let me write down the next page, see whether you agree with this. And anyway, I think did I get this correctly? What is RXY? Sigma. What was C? sigma x squared. Oh, let me simplify this. I am going to, rather than waste your time, let me, if I am getting this,
Professor, I think C is wrong.
what is wrong? C?
Yes.
Why is that? Let me see. Yeah, there is a sigma s squared extra, I think. Look at C. Okay, so let's see here. So you have to, when you multiply by RXS inverse, remember this into this, so you have this. Yeah, I forgot a sigma s squared here. So C sigma s squared. Here it doesn't matter, the conclusions are still the same. That's good. So when you come here, I needed that's why something was wrong. So there is a sigma s squared here. So sigma s squared is, let me do, sigma 2 squared is sigma s squared. You can do this at home. So to me, it looks like sigma s squared multiplied by sigma n squared plus sigma w squared. So anything cancels here, let's see, sigma s squared, sigma n squared cancels. Sigma squared, sigma w squared cancels. So this is gone. Then you get this, and the denominator is sigma squared. So this is sigma squared, sigma, this is gone now. N squared sigma w squared. Yeah, this is, I remember, this is the expression you should get. W squared. So I'm going to rewrite this as by, to bring it into the, I'm going to divide by this quantity, so by this quantity, so that this becomes, okay, so this is the error in the second case. Let me go back and get the error from the other case. Where was it? So that was sigma s squared, sigma n squared over, that's this error. Sigma s squared plus sigma n squared. So I can write this as sigma s squared, I'm going to leave it there. Divide by sigma n squared, I get 1 plus. See, now you can compare this. You see, here in the denominator, you have more terms. This denominator, you only have 1 over sigma 1 squared. This is larger. So this term is larger. I'm sorry, this term is larger. Everything else is the same. So you can see this quantity, this is smaller. So this is what I expect you to do. You can see it takes a little bit of time and so on. So let me give you a couple more problems. I think all these problems are solved in detail on in the YouTube. You just have to find out. So why don't you try to do some of these problems? I'll make up some problem which you can do in the exam, okay? So this is another problem. This is problem 1. This is problem 2. Problem 3 may be x1 is s plus n. x2 is n plus w plus some other noise u. I mean, both are uncorrelated, etc. Another case is I can bring in one more sensor, but that becomes but this is S plus N. This becomes, let's say, multiplicative noise, or S plus NW. So how do you, so try to do these problems. So you have to, the complicated case is what I did, the second case, matrix multiplication, etc. All right, so this has been a lot of time, so I'm going to stop here unless you have any questions. Anyone?
Professor,
Yeah.
so we should make the corona matrix. So how can we find the resource for collecting data?
Where were you last week? I gave you 4 books to read.
I mean the corona matrix. So
What?
we need to find a corona matrix.
What matrix?
Coronavirus matrix. You just yeah. So
All right. So it is I'm too tired now to talk about it. Let's talk next week. Oh, so I had to, yeah, that's a whole different topic. So maybe we'll talk next Sunday.
I mean so we need to collect data to make it.
Yeah, you can do. You don't need my help. Why don't you go and collect a matrix?
I mean it was I tried it, but it was very difficult to find all data online.
Remember, if you cannot find, what do you want me to do? There's nothing. I mean, you can look at the government has published data. You collect as much as data possible. You can work with your friends. You guys don't want to do any work. What am I supposed to do? You have to the city. I mean, if you check on the web, there are lots of places where they have given data. I'm not saying you go. Idea. Look, you need a matrix. That means the number of deaths in each city. Take US or take the whole world. It doesn't matter. Take about 20 or 30 cities, or 20 or 30 countries, and that will be on the column. The rows will be. You have to think about it. How to collect the data. One obvious way is by age, 0 to 10, 10 to 20, 20 to 30, 30 to 40 groups, etc. Or by some, yeah.
I'm sorry. So just could I just collect one country? So I think so.
Yeah, you can also do it. Maybe easiest one. So I'm saying easiest one is country. So make it New York City, San Francisco, and put all the US cities if you want. But you can also put a city like Wuhan. If you know what data from Wuhan, you put it there. It doesn't matter, right? If you know the Italy one city data, you put it there. Here, so the question is how many. So this is New York City, right? So let's say this is age 50 to 60 years. This is over 80 or over 90. This is 0 to 10. I think this data you can get. And then you can see here, maybe you can put income also. People who are low income, high income, if you can split the data somehow. This is high income. I'm just giving, this is easy. You can find a lot of cities. But the question is, you also want a big matrix, reasonably big, right?
Yeah, so it was easy to find the data from cities, but most data are not classified by ages and by incomes.
Yeah, so you need New York City. You can easily find the data. Otherwise, we will not be able to do. If you just give me one, if you say if you just give me everything put together in one column, what are we going to do? So you have to. If you cannot collect the data, then we can't talk about this. You have to. If you can make it into a matrix, then we can think about this problem. So first you see how much data you can collect. If you cannot collect, then why do you want to waste my time?
Yeah, so it was difficult, and honestly.
All right, so you decide. We can discuss, or if you can think of, give me some matrix data, then I will tell you how to improve it. It doesn't have to be this problem, corona problem. If you cannot do it, then you don't have to worry. I'm not going to exam. It is not going to. So you don't have to submit anything if we cannot if we cannot continue with this problem.
Okay.
But why don't you spend one more week and see whether you can collect the data? Okay.
Yes. Yeah.
And if you cannot collect, then we will forget about it. Or if you can tell me some other problem where you can collect data, then we can discuss that problem and make it. So the problem here is, look at this. This is an interesting problem. All the data is going to be non-zero. This is not a positive definite matrix or anything. It won't have any symmetry either. But all the entries will be non-negative. So that's a different kind of matrix. And then you know that it is incomplete, because so the question is, how do you make it better, or how do you estimate it? Some of the data may help you, some other. So maybe the China data may help us other places, or the New York data may help some other column. But to do anything, you need more than row. You give me the whole data, there is nothing. I need to spread the data in a matrix form. Then we can go from there. When I get time, I will also upload these things. So right now, I am going to stop the recording. Okay.